Today we're going to talk about solving systems by the elimination method. So we first talked about how to solve systems with graphing. Next we want to talk about the elimination method. So there's a few steps to go through. So step 1. Multiply, if necessary, one or both equations by a constant so that at least one of the pairs of like terms has opposite coefficients. There's a lot kind of being said in there, but basically we're going to multiply, not always, sometimes none of them, sometimes one of them, sometimes both equations by something so that we get opposite coefficients. And what is opposite coefficients? So we know that a coefficient of 3x is the 3. It's the number that's being multiplied by the variable. So for example, the coefficient 3, if I wanted the opposite coefficient of like terms, well, the like terms would have to be also x's, and the opposite of 3 is negative 3. So that would be a pair of opposite coefficients, 3x and a negative 3x. So then the second step says that we are going to add the equations to eliminate one of the variables. Well, if you think about it, 3x plus a negative 3x becomes 0. So that's where the eliminate comes in. Now you also could subtract, and you might hear that from a future teacher, but in introduction here we're trying to understand the easiest way. The adding is the easiest way, by opposite coefficients. So then step 3 is to solve the resulting equation. Once we've eliminated one of the variables, we want to keep solving so that we get an answer of x equals a number or y equals a number. So then we are going to substitute the value from step 3 into one of the original equations. Now basically, if this sounds familiar, this is what we are doing when we did our substitution method. So there's nothing different from step forward on. We're going to take the answer from the first equation, plug it into one of the originals. And it's important that we go to one of the originals in case we made a mistake when we did that changing part from step 1. Basically, it's the same idea though, to get to find that second variable. And always we should think about doing a check. So let's just see what these look like. So here we have a system. Now clearly I could make a graph. Might make a little bit of a challenge with standard form or trying to get these into slope-intercept form into finding graph paper and straight lines and all that. Could use substitution, but I also would have to now work on getting one of these at least solve for x or for y before I could substitute it in. So the elimination method says if we can find columns, so we want to make sure that our like terms are in columns, and we can see that they are. X's are over x's, y's are over y's. The equals, even is over the equals, and plain old numbers or constants are over each other. So we want to have columns first of our like terms, and then secondly, we want to look for opposite coefficients. So when I look at this first one, I see 3's with 3's. They're the same number, but definitely not opposites. But looking at the y's, I can see opposite coefficients. So I can actually bypass step 1. I don't have to multiply anything. As soon as I see this happening, that tells me move on to step 3 and add these two together. When I'm adding, I'm going to go straight down from top to bottom. I would have 3x plus another 3x is 6x's. The 2x and the negative 2x become 0 or eliminate, and 4 plus a negative 4 is a 0. Now I want to solve the resulting equation, so I got to get x by itself, so I'm going to divide by 6. X equals 0. And remember, I need the x and the y, so I'm going to take this and plug it into one of the equations. I'm going to pick the first one, 3x plus 2y equals 4. When the x is a 0, it goes there. And now I can solve for the y. 3 times 0 is 0. 2y equals 4. When I divide by 2, I get y equals 2. So my answer to this system, remember, is the point that works for both, is going to be 0, 2. So to get to the second one, example 2. So again, we see our like terms in nice columns. That's an important piece. But this time, when I focus on the coefficients, I don't have opposites for these, and I don't have opposites for these. And don't confuse opposites meaning a plus and a minus. The number also has to be the same. So I have a couple of options here. I could focus on the x's and make this negative 10 match this as a positive 10. I could focus on the y's and make this 3 become a positive 6 to match this one. So kind of thinking multiples there. There isn't a right or a wrong way to do this as long as you do this correctly. However, I am going to pick the top equation. So I'm going to say the top equation. And the reason is this. The 3 is positive. The 6 is negative. No, I'm sorry, the negative 6 is negative. So I need the 3 to become a positive 6. So I want to think, by multiplication, how does that happen? Well, if I multiply 2 times 3y, I would get 6y. Now that matches perfectly with this second equation. So remember, the second equation would start out looking like that. And we want this to happen right here. Positive 6y, negative 6y. So here's the thing. If I was to do times 2 to the 3y, I also have to do 2 times everything else in the entire equation. Left side and the right side. And now this kind of looks like I'm doing distributive property, but basically I'm not. It's just showing you that I'm hitting everything. So 2 times a negative 10x is a negative 20x. But I also am going to do 2 times the other side. 2 times 1 is 2. So as long as I multiply everything in the entire equation, both left side and right side, by that number, then it is still the same equation. It just looks a little bit different. And I always kind of say this is what it kind of looks like. If I had 1/2 and I said multiply the numerator and denominator by 2, I would get a new fraction, 2/4. Isn't 2/4 the same thing as 1/2? Yes. If I multiply the numerator and denominator by the number 3, it would be 3/6. But isn't that the same as 1/2? Yes. So we're really kind of doing the same idea, except obviously it's an equation versus a fraction. But as long as I multiply everything, both left side and right side, by that same number, it is still the same equation. So then, once I have this, and that's the key right now, we go ahead and say add these up. Negative 20x and a negative 5x is a negative 25x. These eliminate, and I get 25 on the right. We're going to divide by negative 25 to get x equals negative 1. Now here's the tricky part. Not tricky, but just something to pay attention to. When I go to now plug my x in, we do not want to use this equation that we changed. In case I made a mistake and I didn't change something correctly, we always want to go back to one of the original ones. Doesn't matter which one, but always go back to one of the originals. I'm just going to pick the top one. So negative 10x is now 10 times a negative 1 plus 3y equals 1. That would become 10 plus 3y equals 1. Then we subtract 10. 3y equals negative 9. Divide by 3. Y equals negative 3. And remember, this should work as an entire ordered pair for both equations. So maybe I should do a check. So negative 1, negative 3 is what I think the answer is. So if I plugged in the negative 1, we get positive 10. 3 times a negative 3 is negative 9. 10 plus a negative 9 is 1. that works. This is probably the more important one. Negative 5 times a negative 1 is 5. Negative 6 times a negative 3 is 18. 5 plus 18 is 23. I now know that that is the right answer, so I can kind of 100% confirm we have it. So let's do one last one here where we're looking at trying to write one of these systems and then trying to solve it. So a business with 2 locations buys 7 large delivery vans and 5 small delivery vans. So I'm going to go with this idea right from the beginning. Let's say that the large delivery van is going to be the X's and the small will be the Y's. So that'll just be something to keep an eye on. So location A receives 5 large vans and 2 small vans for a total cost $235,000. Location B receives 2 large vans and 3 small vans for a total of $160,000. What is the total cost of each type of van? So we're looking for the cost of each. So we kind of made this little, verbal model here. So here's the first location. We have 5 large vans at some cost, which we said the large ones were X, plus 2 small vans of the cost of the small van, which we said was Y, that when I multiply 5X, I know the amount of money we spent on large, 2Y, the amount of money I spent on smalls, I know that my bill is $235,000. Then the same thing with cost for location B. 2 vans at the same cost plus 3 vans at the small van cost is only $160,000. So now each of those by themselves is not enough information for me to figure out. But as a system, I can put these 2 things together to find my answer. So here we go. We can have some big numbers, but we'll have to just work through this together. So again, we want opposite coefficients on the X or on the Y. And again, there really isn't a perfectly correct answer to go and which way to go. You could decide to get rid of the X's. You could decide to get rid of the Y's. But basically, when you look at this one, we're going to have a little bit of a situation where we're going to multiply both equations by something. So focusing on 2's and 5's, let's just focus on those for the moment. The first time they would meet as far as multiples would be 10's. So really, I would make one of them a 10 and one of them a negative 10. So it doesn't matter which one you make the 10 or the negative 10. If I focused on these down here, I have a 2 and a 3. Well, the first time they would meet would be at 6. And again, I'm going to make one of them 6's and one of them negative 6's. So I'm just going to focus, really for no particular reason, on the X's and making them 10's. So I'm not going to worry about each equation to each other right now. I'm going to focus on making the top a 10x and the bottom one a negative 10x. So ignoring everything else in the equation, what I need to do is think about how does 5x become a 10x? Well, that happens times 2. That would give me the 10x. So then when I look at the bottom equation, how do I get the negative 10x? It would be times a negative 5. Now once I determine the first piece, now I definitely have to go through and multiply all the rest of them to keep my equations the same. So 2 times 2y is 4y. 2 times also, remember on the other side as well, now I get 470,000. Negative 5 times 2x we said is negative 10x. Negative 5 times 3y is negative 15y. Negative 5 times 160,000 is going to be 800,000. So now we have our new, and it's negative. Got to make sure I catch that, right? It was negative 5 times that. So we have negative 800,000. So now I have those opposite coefficients. We can go ahead and start putting the addition piece here together. And let me just slide this up a little bit so we can see our work. Then, when I do my addition, that eliminates. I get negative 11y, and I get negative 330,000. So now I just solve the rest. Divide by negative 11. That negative 330,000 now becomes positive, and it becomes 30,000. So I now know that the y is 30,000. But then I need to know what the x value is. So again, I'm going to go back and pick one of them to plug in. Well, again, it doesn't matter which one you pick. I'm going to pick a little bit of the smaller numbers and go with the second equation we did. Definitely not that smaller numbers, but we're going to get a little bit smaller. So the 2x we still don't have. The 3 we now know is times 30,000. Then this becomes 2x plus 90,000. We subtract 90,000 from both sides to get 2x equals 70,000. We divide by 2. X equals 35,000. And then, remember, we're in a word problem. So we don't want to just say x is 35,000, y is 30,000. We want to make sure we have a context and we interpret what those numbers mean. So the x was standing for the cost of the large van. So the large van is 35,000. The small van is $30,000. So that's another way to be solving these systems. Definitely will be something that we want to be looking for, this kind of standard form look where we can have like terms and nice columns and then start finding the opposite coefficients. This is the elimination method that will then hopefully go along with your knowledge of the substitution method as well as the graphing method, and hopefully this will go well. If you have any kind of questions, please make sure you let me know at our class next time we see each other.